This is the most extreme scale-up the world has ever done. This is scale-up flops. Hopper is 1. X Blackwell 68X Rubin is 900X scale-up flops. Just when you thought AI was moving fast, Nvidia hit the gas in a single keynote. They revealed a new generation of supercomputers so powerful they can deliver an entire exaflop in one rack. But that's just the start. We're talking about machines that aren't just scaled up. They're completely reimagined, disaggregated and liquid, cooled to pack 600,000 components into one frame. And while the Grace Blackwell system is launching this year, Nvidia is already plotting 2 steps ahead with Vera Rubin and Rubin Ultra pushing performance into unheard-of territory. Meanwhile, they've tackled the massive data bottleneck with Silicon Photonics-built enterprise-ready AI workstations that look like something from a sci-fi lab and unveiled a robotics platform that uses simulated physics to train machines in virtual worlds. This isn't just hardware, this is Nvidia, redefining how AI data centers and even robots will evolve over the next decade. If Hopper was the warm-up act, Grace Blackwell is the main event. What Nvidia just unveiled isn't an incremental step, it's an architectural leap. Grace Blackwell is the first AI supercomputer capable of delivering a full exaflop of performance in a single rack. That's 1,000,000 trillion floating point operations per second from just one tower. And it's not magic, it's the result of rethinking everything: the GPU design, the cooling system, the data throughput, and even the physical layout of the components. Here's how they pulled it off, instead of the old integrated approach. Nvidia disaggregated the NVLink switches, moving them out of the motherboard and into their own dedicated system trays. These now sit at the heart of each compute cluster, allowing every GPU to talk to every other GPU simultaneously at full bandwidth. And by shifting from air cooling to full liquid cooling, they compressed what used to take an entire server room into just one rack housing 600,000 components and pulling 120 kilowatts of power. That's nearly the energy consumption of a full home condensed into a high-efficiency AI engine. But what makes Grace Blackwell so groundbreaking isn't just speed or compression, it's how it changes what AI can actually do. We're entering the era of reasoning AI and agentic systems, which require far more computation than previous models. The demand has grown 100-fold in just the last year. Grace Blackwell doesn't just keep up, it unlocks possibilities we couldn't even touch before. From training multi-trillion parameter models to powering next-gen inference tasks in real time. This system isn't just a performance bump. It's the backbone for AI's next major leap. Just as Grace Blackwell begins production, Nvidia is already preparing for its successors. The company's roadmap is moving with precision, speed, and ambition, ushering in the next phases of computing with the Vera Rubin and Rubin Ultra architectures. If Blackwell was about building the exaflop machine, Rubin is about multiplying that by 15 and scaling the future of AI infrastructure beyond what seemed feasible just a year ago. Named after the astronomer who discovered dark matter, Vera Rubin is scheduled for release in 2026 and represents an entirely new ecosystem. We're talking brand new CPUs, brand new GPUs, HBM4 memory, a new NVLink 6 architecture, and next-gen networking components like CX9, Smart NICs. All of it is designed to fit into the same rack architecture as Blackwell, but everything inside has been redesigned from the ground up. Rubin's CPU, for example, delivers twice the performance of Grace while consuming just 50 W. It's the kind of power-to-performance ratio that turns heads in the enterprise world. But the real showstopper is Rubin Ultra, arriving in 2027. This isn't just a step forward, it's an exponential jump. Rubin Ultra boasts a jaw-dropping 15 exaflops per rack powered by 2.5 million parts and pushing an eye-watering 4.6 petabytes per second of bandwidth. For comparison, that's 4,600 tab moving every second through a single rack, and none of this is theoretical. This is scale-up bandwidth, not aggregate, meaning every GPU is getting direct high-speed access at levels we've never seen before. To make this kind of scale viable, Nvidia had to rethink packaging and component density. Each Rubin Ultra is built to handle 600 kilowatts, that's 5 times more than the already intense Blackwell rack. The number of GPUs is massive, and many are multi-D packages containing 4 GPUs in a single assembly to keep them running efficiently. Everything is cooled using next-gen liquid systems and controlled through finely tuned switch networks with unprecedented precision. This roadmap isn't just aggressive, it's deliberate. Nvidia is planning every step 2 to 3 years ahead, ensuring that infrastructure partners, cloud providers, and enterprises have time to adapt. Each generation introduces radical performance gains while keeping one foot grounded in established design. The chassis remains constant, but everything inside evolves. This modular approach allows Nvidia to take massive innovation risks in GPU, CPU, and networking design without destabilizing the overall ecosystem at its core. Rubin and Rubin Ultra are about breaking the ceiling. The AI workloads of tomorrow, true general intelligence, real-time robotics, agentic reasoning models, will demand not just fast processors, but seamless orchestration across hundreds of thousands of GPUs. That's the world Rubin is being built for, and with every detail from transistor count to interconnect bandwidth optimized for scale. Nvidia isn't just predicting the future, they're building the hardware that will power it. Scaling up gets you incredible performance inside a rack. But scaling out, connecting hundreds of racks across a data center, introduces a whole new set of engineering challenges. Traditional copper cabling hits a wall. When distances grow, you lose signal, integrity, waste energy, and drive up costs. For a world aiming to link millions of GPUs across massive AI factories, copper simply isn't enough. That's where Nvidia's silicon photonics breakthrough comes in. Instead of relying on energy-hungry transceivers that consume 180 watts per GPU, Nvidia engineered a new solution based on micro-ring resonator modulators, tiny energy-efficient devices that modulate light directly on silicon. By stacking these photonic chips with traditional electronics, Nvidia created a coaxial optical system that eliminates the need for bulky transceivers and slashes energy usage. The result, an optical switch with 1.6 terabits per second of bandwidth, ready to scale AI systems to hundreds of thousands, even millions of GPUs. It's a foundational shift that makes the massive scale of Rubin Ultra possible without melting down a power grid. But Nvidia isn't just thinking about cloud giants and hyperscalers. They're also turning their attention to desks, labs, and offices around the world. Enter the DJX Station, a personal AI workstation that brings the power of a supercompute into a machine the size of a desktop, with 20 petaflops of performance, 72 CPU cores, and high bandwidth HBM memory. This isn't your average PC. It's built for data scientists, AI developers, and research teams who need cutting-edge performance without waiting in cloud queues. What makes the DJX Station especially impressive is its accessibility, manufactured by partners like Dell, HP, Lenovo, and Asus. These workstations are designed to be widely available, and while they come packed with Nvidia's most advanced chips, they're also modular enough to include consumer-grade GeForce cards via PCIe. Perfect for experimentation, simulation, and high-end rendering. It's a signal that Nvidia doesn't just want to power the cloud, they want to empower the creators on the ground floor of innovation. And speaking of innovation, nothing showcases Nvidia's vision more clearly than its push into robotics, with billions of sensors now embedded in warehouses, factories, and vehicles. Every piece of infrastructure is becoming robotic, but training physical robots requires more than code. It needs a virtual world where those machines can learn, adapt, and fail safely. That's why Nvidia created Omniverse, their real-time simulation platform. It's like an operating system for physical AI, combining virtual environments with generative AI to simulate infinite variations of the real world. The engine behind this, a model called Cosmos, a generative AI that understands physical environments and can create endless training data by combining Omniverse with Cosmos. Nvidia allows robots to explore new scenarios, test actions, and refine behavior without ever touching a physical surface. And it doesn't stop there. They've also introduced a GPU-accelerated physics engine that provides verifiable real-time physical feedback, something essential for teaching robots fine motor skills and tactile response. In short, Nvidia is building a full-stack system for developing general-purpose robots from perception to action, trained entirely in simulation before ever hitting the floor. What ties all of this together is a single cohesive strategy: build vertically integrated platforms for every layer of AI, from the server room to the workstation, from silicon to software, and from simulation to the real world. Whether you're connecting racks with light, building the next AI model at your desk, or training a robot in a synthetic warehouse, Nvidia wants to power it all. And judging by the pace of their roadmap, they're not just participating in the AI revolution. They're leading it. What we're witnessing isn't just an upgrade cycle. It's a redefinition of what's possible in computing. Nvidia has moved far beyond making graphics cards. They're now the architects of the infrastructure that will drive the next industrial revolution, a revolution not built in factories, but in data centers, research labs, robotic warehouses, and AI training loops running at exaflop speeds. The Grace Blackwell supercomputers are just the starting line, packing 600,000 components into a single rack, and delivering 1,000,000 trillion operations per second would have sounded impossible just a few years ago now. It's a shipping product, and while the rest of the industry is still catching up to that announcement, Nvidia is already preparing to leap forward with Vera Rubin and Rubin Ultra systems that will push performance by 15x move per bytes of data per second, and power the kind of AI models that can simulate language, biology, economics, and even human reasoning with unprecedented depth. But this roadmap isn't about brute force alone. It's about elegance, about solving the bottlenecks of connectivity, energy efficiency, and scale. Nvidia's innovations in silicon photonics are just as critical as the chips themselves by swapping out bulky power. Hungry transceivers for laser-based interconnects built on micro-ring modulators. They're creating an AI network stack that's leaner, faster, and ready for global deployment. This isn't just a hardware trick. It's a systems-level rethink of how data moves, processes, synchronize, and workloads scale. And they're not stopping at data centers. The DGX station puts Pedlop-class AI directly into the hands of researchers, engineers, creators, and innovators. It makes the future more accessible, more personal, and more democratized. When you give this level of power to a scientist working on genomics, or to an artist training generative media, or to a student pushing boundaries in robotics, you accelerate the timeline of discovery itself. That's what Nvidia understands so well. Infrastructure doesn't just enable computing, it shapes the pace of human progress, which brings us to perhaps the most audacious part of their vision. Robots, not just toy robots or factory arms, but adaptable, intelligent, general-purpose machines trained in virtual worlds and grounded in real physics through Omniverse and Cosmos. Nvidia is giving birth to synthetic environments where AIs can learn like humans by doing, by failing, by adjusting, and by mastering context. These aren't just simulations. They're mirrors of reality governed by high-fidelity physics engines running in GPU-accelerated time. Every action a robot takes in that world refines its intelligence until it can operate with skill in hours. Put all of this together, supercomputers that redefine hardware limits, a roadmap scaling from desktops to planetary infrastructure optics, replacing copper robots trained in simulation. And it's clear Nvidia isn't just delivering faster chips, they're laying down the digital rails for the next century. They're building AI factories, robotic ecosystems, and simulation-powered learning loops that collapse the boundaries between hardware, software, and intelligence. This isn't optional innovation, it's structural. Every major leap in AI, from language models and image generation to autonomous systems and scientific discovery, will be built on top of the infrastructure Nvidia is rolling out today, and the companies, researchers, and governments that align with this pace will be the ones leading tomorrow's breakthroughs. So the next time someone asks, what's next for AI? You'll know it's already being built in racks, humming with trillions of transistors, in photonic circuits pulsing with light, in robots dreaming in simulation, and in the relentless roadmap of a company that doesn't just imagine the future, it engineers it.